Welcome back. So this will be my second lecture, and this one will be very different from the first one. It will be also dealing with the topic of multi-component superfluidity and superconductivity, which Raphael discussed, but in a sense orthogonal. It will be all about Raphael refused to discuss, mainly multi-band superconductivity.
I refuse, I let you.
Okay, sure. Okay, very good. That's the deal. So essentially, multi-components can be of two kinds, and both are compatible with each other. So for simplicity, think of, say, bosonic superfluidity when you have n species of bosons. Each of the species can have its internal degrees of freedom. And those internal degrees of freedom can be treated as components, and that's essentially what Raphael was discussing. Yet another kind of aspect of multi-components that we have n species, and each of them is an individual field in the sense that the Hamiltonian is U1 invariant with respect to the global phase of each of the fields. So essentially, the key aspect for me is that we have more than one superfluid phases, more than one phases which are responsible for the superfluid order. And that's essentially the setup. But obviously, I'm not going to discuss something trivial like just a mixture of n-component superfluid fields. I'm going to discuss something more delicate. And actually, there is a motivating experiment, a recent motivating experiment, which I will ultimately be explaining, because if I just show you the paper which reported the observation of the state with spontaneously broken time reversal symmetry above the superconducting phase, so kind of this fact tells you nothing about the structure of the phase. So I'm talking of this observation of what was called quartic metal in this paper. So essentially what was observed that at a certain level of doping and a certain high enough temperature, the superconducting phase, which is quite interesting on its own because it features broken time reversal symmetry, experiences a phase transition to the normal state, which actually still features broken time reversal symmetry. And my point is that there is something interesting in the structure of this phase. So if we think generically of the broken time reversal, we can say, okay, it's just some broken Z2 symmetry, because time reversal is a type of Z2 symmetry. So if we have two domains, as always in the break Z2, we can have two different domains. There would be a domain wall between the two, and this domain wall would be unique in a generic case. So here, we are supposed to see three different domain walls, which kind of a non-trivial fact, and essentially the macroscopic nature of this fact is reminiscent of sort of topological ordering. Like in topological insulators, the bulk is boring insulator, but the surface reveals the ordering. Here, instead of the surface, we can discuss the domain wall and observe that actually the domain wall, there are three different domain walls. So meaning that there is some kind of hidden structure behind this broken time reversal. And actually, this hidden structure is directly relevant, originates, if you will, from the counterflow ordering plus Josephson coupling, which destroys this counterflow ordering in a very controlled way. So kind of the story will start with just counterflow ordering, which is interesting on its own. So what is counterflow ordering? So suppose we have n components in the sense in which I define them. So kind of I'm refusing to discuss Raphael's physics. So my components on its own are very boring, no internal degrees of freedom at all, so n components. And suppose for a certain reason, which I will explain on the next slide, the individual orders are absent. So there is no broken U1 for each component separately, but somehow there are order parameters of this structure. In two components, you can say, oh, it is reminiscent of the spin ordering. Yes, for two components, it's reminiscent of spin ordering, but let me tell you upfront that two components is not the most interesting thing. The most interesting thing is 3 and more components. We will see the qualitative difference. So those guys appear, and as I already said, that I really care about real superfluid phases. In this sense, I'm not going to say that helium-4 is a composite order consisting of 6 fermions. No, for me, only the effective field, which is a carrier of the superfluid phase, matters. So if you have a situation like that, we have something which is reminiscent of superfluidity, because superfluidity is all about broken U1. So the moment we have broken U1, we have a phase. Now it's the phase of this correlator. It's still a complex object. And we can twist this phase. By the way, I want to tell you right away that those psi's can be bosonic field operator, then can be classical fields, and can be even fermionic operators. In which case, if we have more than 2 components, say 3 components, it's a non-trivial order because it does not involve sort of individual pairing. So typically when we are talking of fermionic superfluidity or superconductivity, we are talking of Cooper pairs which behave like bosons. Now we have just those order parameters consisting of two fermionic operators. They are not independent, meaning that this order cannot be just reduced to pairing. It's something less trivial if the number of components is more than 2. So whenever we have a phase, we can twist it. That's essentially the essence of superfluidity. That's how we get persistent currents. If we twist the phase, it's topology. The phase cannot be untwisted. And that's how we end up with persistent current states in a toroidal geometry. And of course, now comes a question, how do we get, what is the scenario of getting this type of ordering, which we call counterflow ordering. As we will see, this ordering corresponds to the counterflow motion of components. Well, there are 2 scenarios which were suggested more or less simultaneously, at least within 1 year. Yegor Babayev published, he prefers to cite his preprint. There is also a published paper, but preprint came earlier. So essentially, it was one and the same year, 2002, when Yegor Babayev suggested a scenario, which I will be discussing a little bit later, which is based on finite temperature proliferation of vortices. And Anatoly Kukov and yours truly proposed a different scenario, which is based on Motness. So let us start with this Motness scenario.
Boris,
yeah.
Sure, very quickly, just to set the stage, you don't have any, there's no Josephson coupling yet between the constants.
Exactly. It will show up later.
So
Exactly.
U1
Yes, exactly. No, forget about Josephson coupling. It will show up later. Let us discuss counterflow superfluidity as is, without any Josephson coupling. We will introduce it later. Stay tuned. So for a while, we'll be discussing just counterflow superfluidity. So actually, this is a very well-known super exchange mechanism. So suppose we have a system on a lattice, a system which consists of either bosons, or all our components are either bosons or fermions. It's not a mixture of bosons and fermions. And then suppose the repulsion between particles is strong enough, and we have the filling factor which is commensurate. For simplicity, just unity can be 2, and 3 should be commensurate. It's the total filling factor. Individual filling factors are different, can be equal to each other, can be different, doesn't matter. What matters is that in total, we have a commensurate filling, which leads to Motness if the interaction is very strong. we are in a regime when the net flow of particles is just suppressed, arrested by mootness. However, what is allowed, and this is a very well-known textbook mechanism known as super exchange, is the following virtual process. So if you have two different particles on nearest neighbor sites, then one of the two can hop, there will be a doubling, and then if the other guy hops back, we have an exchange between the two. It's the standard mechanism of how you derive, say, the Heisenberg model out of Hubbard model, in which case the interpretation of blue and red is spin up and spin down. It's how you do the flip-flop. But the point is that this super exchange applies not necessarily to a two-component system. It can apply to any component system. So essentially, that's the mechanism of counterflow. The net hopping is arrested. So essentially, if we write the effective Hamiltonian, projected Hamiltonian by excluding this type of states, then we end up with the super exchange hoppings, when just two particles of two different colors exchange the occupation of the nearest neighbor site. And this is precisely what leads to the counterflow superfluidity, because if we do the calculation, we will see that if the particles are fermions, then essentially the effective Hamiltonian, at least in terms of two components, it's a spin Hamiltonian. Now we need to make, with fermions, we need to be accurate, because you see, often if it's just on-site interaction with fermions, we have a high symmetry instead of U1 cross U1 cross U1. And times we can get SUN, and that's what we don't want to get. We want to suppress SUN down to U1 cross U1 cross U1 n times U1 to the power n. And this can be done by just introducing nearest neighbor interaction in the case of fermions. It just should be more accurate. Or it can be achieved by non-equal population of the components. Say if instead of taking in a two-component system, for example, which is equivalent to the Heisenberg model, if the spin up and spin down occupation are non-equal, then it's pretty much the same effect as breaking SU2. But for simplicity, just think of nearest neighbor interaction, which suppresses the kind of higher SUN symmetry. Okay, so Bromance superfluidity. I already mentioned the fact that the case of 3 and more components is far more interesting, because somehow we cannot reduce, because those order parameters are sort of related to each other. If we have just two components, we are left with just one order parameter, right? Because it's just one combination of the two fields, which is non-zero, meaning that qualitatively, the system, which is a counterfluid consisting of two components, is equivalent to the single component superfluidity. We do not get a new quality. A new quality, which we call Bromian supercounterfluidity, emerges when we have 3 or more components, in which case we need actually somehow to classify, to understand this order. When we have, because you see, if we have n components, we can form order n squared pairs, but obviously out of n components, we cannot have n square independent orders. So somehow the orders are depend on each other, and the idea is to understand how to come up with classification of independent order parameters. So everything is reminiscent of the Bromian rings, when somehow guys are related to each other, are important for each other. And actually, let me explain the qualitative difference between 2 and 3 or more. So you see, if we have just two components, as I said, everything is equivalent to a single component system, because now we have a phase which is a relative phase. So when I write here 1 and 2, it's a kind of very loose language. So what is actually well defined is the phase twist between 1 and 2, the relative phase twist. And when we have just two components, this relative winding is just the only topological number which we have, a multiple of 2 pi, as if we have just one component. However, if we have 3 and more, the elementary topological excitation has a different structure, because now we can take one component, say component 1, and phase twist it with respect to other 2. And the other 2 are not phase twisted with respect to, the to each other, meaning that now we have sort of a reference frame with respect to which a phase of one of the components gets twisted. Meaning that while here we have only one up to the sign elementary, say elementary vortex or elementary supercurrent state in a toroidal geometry, here we have n. So essentially, interestingly, we hop from 1 to 3 immediately, and this is the manifestation of this kind of Borromean type, when essentially we have n components and n elementary vortices, which is sort of non-trivial because you see we have suppressed one mode. Obviously, in terms of the phonons, in terms of the Goldstone modes, we would have only n-1 modes because one mode is suppressed. Meanwhile, in terms of the elementary topological excitations, we would have n. So this mismatch between the number of Goldstone modes and the number of elementary topological excitations is a sort of hallmark of what we call Borromean ordering. By the way, do not hesitate to ask questions if you have some. So in the general case, it's just the same, but for n components. So if we have more than 3 components, we still have the same picture. We have all components but one which are not phase twisted with respect to each other, and one component which is phase twisted with respect to the rest of the components. So an alternative mechanism, I promised to describe the mechanism proposed by Yegor Babayev, and now it's time to describe it. So we were talking of zero temperature mechanism of Mottness, but there is a finite temperature mechanism, and it's best illustrated by this idea by Yegor, dealing with a stack of two-dimensional superconductors. So I presume that you all know the academic fact that in 2D there is no superconductivity at any finite temperature because the energy of a single vortex, as opposed to the superfluid, where the energy of a single vortex is infinite, logarithmically diverges with the system size. In a superconductor, it's finite because of the screening effect. It's finite but pretty large, meaning that for all practical purposes, though there is no phase transition there is no BKT phase transition, everyone discusses it because essentially it's a very sharp crossover. So there is a characteristic temperature at which the system becomes superconducting for all practical purposes in 2D. But still, academically speaking, if we have finite temperature two-dimensional superconductor, it's normal. Now, if we have a stack of superconductors, 2 or more two-dimensional superconductors, we can ask the following question. So suppose we have proliferated vortex in one of the superconductors. What will happen to the rest of the layers? Because you see, the screening of the vortex means it's screened by the magnetic field. It means that there is a magnetic flux attached to this vortex. And the layer nearby, actually all the layers nearby will be filling this flux. And this flux will create an infinite energy, meaning that if we have a multi-layer, 2, 3, 4 layer two-dimensional superconductors, we cannot just proliferate a vortex in one of them. We have to proliferate a sort of composite vortex which is a vortex in each of them, in which case this vortex will be screened, and essentially that's the scenario. This is the scenario of proliferation of composite vortices. Now, if we proliferate a composite vortex in all the layers, we cannot still suppress the counterflow, because if you think of the counterflow order, which corresponds to the phase difference, you can immediately see that if we take the vortex, the composite vortex, in a vortex in each of the layers from one side to another, we will actually untwist one of the phases, but we will further twist the other one, meaning that the relative phase twist cannot be changed. So kind of the relative phase twist is immune to proliferation of those vortices. So the system still supports counterflows. They are neutral, because if you have a flow in one layer, there will be a counterflow in the other layer. In the electric sense, there is no electric current, net electric current. They're just counterflowing currents. That's the scenario, which actually converts a stack of two-dimensional superconductors into the neutral supercounterfluid. We call those systems supercounterfluids. Another example, we can actually combine the two cases. So suppose we are back to our scenario with Anatoly Kuklov, where we have modness, and suppose we dope a system a little bit. We actually make our filling factor not exactly 1 by, say, 0.9 or 1.1, in which case, if it's a bosonic system, it becomes just an n-component superfluid. And then we increase the temperature. And then Yegor's scenario of proliferation of vortices comes into place. So essentially, as a result of raising the temperature, we will kill the superfluidity of the net superflow, and we will end up once again with the counterflow regime. Actually, if you want more examples, just look into the chapter 6 of our book with Yegor Babayev and Nikolai Prokofiev. Kind of in this chapter is all about multi-component in the sense in which I introduce it, in the sense of more than one superfluid phases. There will be a generic discussion and some review of earlier publications. So now what I want to discuss with you is our recent work with Yegor, because somehow it's interesting that the discussion of multi-component superfluids began quite a while ago, about 2 decades ago, but until very recently, until this work which you see over here, which was submitted in November, I believe, people were not discussing the hydrodynamic description of counterflow superfluidity with more than 2 components, because as I said, with two components, it's pretty much the same as with one component. Meanwhile, hydrodynamic description is the essence of the theory of superfluidity, because it's a universal description of all superfluids. So some crucial ingredient was lacking. And let me introduce you to kind of to the hydrodynamic Hamiltonian. So the hydrodynamic Hamiltonian is the effective, essentially classical field. Of course, you can quantize it, essentially classical field Hamiltonian model describing the long wave, universal long wave properties of superfluids. In our case, counterflow superfluids. And the most interesting case, of course, is the Bromian counterfluid. Yeah?
So before you move on, I was just curious about one thing. So you're talking about the relative phase.
Right.
But what about, you can also have the global phase of both, in other words, like a quartet which actually breaks gauge invariance as well.
global phase of what, excuse me?
What I'm saying, instead of psi alpha, psi star beta, you could have just psi alpha, psi beta, without the star.
Psi?
Yeah.
Oh, in principle, I could have it. It would correspond to something like pairing.
Exactly.
That's yet another alternative, which I'm not discussing here, but it's possible, right? But
my question is, if you compare both, which one usually emerges first? Because I'm thinking of the papers by Nozier and so on, where they're talking about pairs of bosons.
Oh, that's also possible, but in my case, it's really psi dagger or psi star if it's a classical field because of the Motness. Motness requires that everything moves in the opposite direction. Or say Yegor's scenario, when you proliferate vortices, you naturally move in the opposite direction, because otherwise, if you move in the same direction, then you can unwind your global winding. So you really need this counterflow so that you cannot unwind it. So there are different reasons. So Yegor's scenario and our scenario, they are microscopically different, by they lead to one and the same bottom line. You cannot unwind. Your counterflow is protected, but coflow is not. In our case, coflow is just absent if we are talking of Motness. If we are talking of the upgrade, when we dope the system, then finite temperature just kills the coherence of the coflow motion. But in principle, such orders can also exist. It's just not what I'm discussing. Okay. What we are going to do, we are going to guess the hydrodynamic Hamiltonian, which corresponds to the Borromean counterfluids, and then just check by inspection that our guess is correct. That's typically the approach. So we need to come with something. Of course, we do understand that the hydrodynamic Hamiltonian should be written. We do understand the canonical variables. The canonical variables are the superfluid phases and canonically conjugate variables, which are deviation from density. So we do know the structure of canonical variables. We just need to figure out what is the structure of the Hamiltonian. Which actually seems to be something weird, because you see, microscopically, we do see the reason for arresting of the net flow. We understand that the macroscopic Hamiltonian has to be translationally invariant. And the question comes, is it actually possible to come up with something which is translationally invariant, which sort of arrests the net flow? Is it possible? Seems impossible, but think of a superconductor. The bulk of the superconductor is sort of insulator, because if you think of superconductivity, it's a surface effect. The Meissner effect kills superconductivity in the bulk. So it's an important hint that the actually gauge invariance kills, it's essentially Anderson's effect. Gauge invariance kills everything, kills all the non-trivial motion, including the Goldson mode in the bulk of a superconductor. So meaning that if we are talking of a gauge theory, then we can expect that somehow the gauge invariance can kill the net motion. And this is precisely what we are going to see in our theory. But the inspiration comes from this finite temperature idea by Yegor and collaborators, that if you have a finite temperature, that would be the generic form for the effective free energy of a multi-component superfluid. So this free energy is not for the counterfluid yet. It's just for the multi-component superfluid when the phase is defined at least microscopically. And what's written is actually generic form. It's an absolutely generic form. It implies only that there is a symmetry between components in terms of their properties. So all the components are similar to each other. That's why there are only two coefficients in this Hamiltonian. But essentially, the Hamiltonian has to be quadratic because it's gradient expansion. Hamiltonian free energy, free energy density. It should be positive definite, quadratic. It should be expressed in terms of the gradients of the phases, the gradient expansion. And you can always cast it in the following form, just by regrouping the terms. And then suppose that this term, this actually coefficient, is very small for a certain reason, vanishingly small. And then if you have a finite temperature, then the smallness of this guy will tell us that it's energetically favorable to proliferate the composite vortices. So the proliferation of composite vortices will actually convert this system at high enough temperature into the phase of counterflow superfluidity. And then comes a guess. What if actually this is precisely the structure of the term, when we kind of remove this guy, of the term in the hydrodynamic Hamiltonian, so that the hydrodynamic Hamiltonian should have a structure like that. And as I already hinted, we need a structure which features gauge invariance. So, yeah?
How important is that you have the same stiffness for all species?
Good question. Absolutely irrelevant. On the next slide, you will see that all the stiffnesses are different.
Okay.
It's absolutely irrelevant.
Okay.
What is relevant is that, it's an excellent question. What is relevant is that we have only those phase differences and nothing beyond that. Those coefficients can be anything. So that's our guess for the structure of the Hamiltonian. So of course, we can also write a nonlinear hydrodynamic Hamiltonian, and I will do it a bit later. There is no problem. Once we understand the principle, we will immediately write the Hamiltonian. So I just deliberately started with the bilinearized Hamiltonian corresponding to the long wave motion. So we guess this term, which is written in terms of squares of the difference of the gradients, and kind of by canonicity, if you will, the term which is written in terms of the deviations of the density should have the following. This guy is standard. If we would have an n-component superfluid, we would write this term in this particular form. So nothing special about this term. The fact that these guys canonically conjugate to the field of phase is just the microscopic property. So the trick is just to write the phase gradient term in this kind of very special form. You will see why it's special in a short while. So now let us just check that our guess is correct, that the net flow is arrested. We need to write down the Hamiltonian equations of motion. It's a pair of equations for each component. That's the equation for the deviations of density. That's the equation for the time derivatives of phases. And now if we sum up all those equations, we will see that actually they sum up to the following nice equation telling us that the net density does not evolve. It's arrested. So kind of our guess was correct. So with this structure, the net density is arrested. And this is consistent with the requirement that the net density is constant. Of course, formally, mathematically, we can say whatever we start with in terms of the net density in this Hamiltonian, it stays the same. But physically, we understand that we are supposed to start with the situation when the deviation of the net density is just 0. Right? It's just modness, right? So everything is nice, it's consistent. So that's the proof that this Hamiltonian indeed captures the counterflow hydrodynamics. The net flow is arrested, very good. So obviously it's guaranteed that kind of one of the phonon modes, one of the sound modes will be trivial. It just corresponds to the absence of any motion. And it's also good to see that each of the equations can be cast in the form of the continuity equations, meaning that essentially we can introduce explicitly from this Hamiltonian the notion of the current of the component alpha. And you see, this expression for the current tells us that we are dealing with the kind of non-trivial situation of severe drag, because the current of the component alpha depends on the phase gradient of not only of the phase gradient of alpha, which would be normal, which is kind of standard situation with a single component superfluid, when the current is proportional to the gradient of phase, but it's actually a difference of the phases. very non-trivial structure. And all the currents sum up to 0. Now, what is kind of the property? Because you see, this looks like a local constant of motion, right? There are no integrals. Local constant of motion. Local constant of motion typically is supposed to follow from some local symmetry. And this local symmetry is nothing else than what we call compact gauge invariance. So in a standard gauge invariance, we just add some phase field to all the phases of all the components. The compact gauge invariance, as opposed to kind of standard gauge invariance, allows us to add not only the regular field, but also the field with topological defects. So this field which we add is allowed to have topological defects, because whatever we add, so you see, whatever we add will be just subtracted. And this is really important. And later I will elaborate on it, why it's important to speak of just compact gauge invariance as opposed to standard gauge invariance, where, for example, we cannot gauge out a vortex. So this gauge invariance allows us to gauge out a vortex if it's a global vortex in all the components. So actually, we have a local continuous symmetry, and then by Noether's theorem, we have this constant of motion. So essentially, they arrest. So we have a kind of we have an interesting type of gauge theory without gauge fields. So it's a kind of a new type. To the best of our knowledge, it's a new type of gauge theory when there is gauge invariance, even stronger gauge invariance in this sense, because we can add a field with defects, compact field, in the absence of gauge fields, a kind of intrinsic gauge invariance. And then we have a Noether's constant of motion, which precisely what we need, the constant of motion, which arrests the net flow. A signature feature of this compact gauge invariance is the classification of the defects, because we end up with something which we could call modular arithmetic of topological charges. So think of the following. So suppose I have a vortex, which is an elementary vortex or non-elementary, and I have a system of vortices, and I ask a pretty standard question. So if I have a local system of vortices, what am I going to observe if I go far away and just make a circle, calculate the topological invariance? What am I going to observe? To observe. So in the case of single components, we just do an algebraic sum of topological charges, and whatever it is, that would be the topological charge of our system. Like if we have a vortex loop, it will be 0. If it's just, say, in 2D, it's vortex and vortex pair, it will be 0 as well. Here, because of the compact gauge invariance, we have sort of interesting phenomenon when we are supposed to sum everything by modular this vector. So that's the idea of classification of the topological charges. So I pretend that the winding of each individual phase exists and is a multiple of 2 pi. So this integer m1, m2, and those integers are corresponding integer winding numbers. So obviously, I do something which is not quite well defined, because those guys are not gauge, compact gauge invariance. But to fix the issue, I just need to realize that I'm supposed to compare those guys modular this vector. So essentially, this is precisely the result, if you will, of compact gauge invariance, when I can actually add at will any topological defect of this structure, when I wind simultaneously all the guys. Yeah?
What kind of boundary conditions do you need to impose to get to this point, or it's not?
It has nothing to do with boundary conditions. It's all about the bulk properties.
I understand it was more like a question to when you define your continuity equation and everything. So the geometry or topology of the manifold will work is not really important.
No, because it's not important. Well, of course, if I solve the equations of motion, I do need to introduce the boundary conditions. It can be periodic boundary condition, or if I am talking of topological defects, I need kind of periodic boundary condition, the topology of torus and stuff and stuff. But differential equations themselves, they do not depend on the boundary condition. So, yeah.
Just so I understand this,
Yeah.
engaging variance more, this 5R is, when you say it's not single value, does that mean like it's?
What is this? What is this? What is this? What is this?
Well, it's like a scalar. It's a scalar that you.
It's a scalar, but it's, so let me remind you what we mean by compactness. By compactness, we mean non-single valuedness of the field of phase. It's defined modulo 2 pi.
Okay, so that every point in space of this phi field can have plus or minus like an integer multiple of 2 pi?
You can have any number of vortices, vortex loops, and stuff. So it's something which has a well-defined gradient, but not the values. Think of a single vortex.
Is it smooth?
Hmm?
Is it smooth?
It's smooth apart from the cores of vortices. The gradient is smooth. The gradient is smooth everywhere apart from the cores of the vortices. Okay? But think of the 2 pi winding. The gradient is smooth, but you do a winding, and you integrate the gradient, and you get 2 pi, right? This is the essence of superfluidity. You go around your torus, you integrate gradient, it's smooth and nice, you integrate, you do the path integral, and you end up with 2 pi times 100, a multiple of 2 pi. So because the phase is defined modulo 2 pi.
Would any holomorphic function work for that?
Say it again?
Would any holomorphic function work for that? Some regular part divided by pole.
All right, but we have zeros rather than poles, because you see typically when you have a vortex, you end up with 0 rather than a pole. But the structure of the phase is pretty much the same. You do a winding, right? Yeah. But my point is, yeah, that makes sense.
So there's like, sorry, I think maybe, yeah, but there's like line defects, I guess.
Yes, line defects this guy will be ill-defined on a line, but on this line, but this line has no physical meaning. Let's put it this way.
Okay.
So there is a line with no physical meaning. So that's the point. So yeah. So the vortex in this guy has absolutely no physical meaning. That's my point. Because you see, and the reason for that is that those phases, individual phases, do not have a physical meaning. Only their differences. But if I add something which has no physical meaning and then subtract, I need to show you the equation. You see, we have phase differences. So I add something without physical meaning to this guy and immediately subtract this very, very same something. That's how it works. So whatever you add, you immediately subtract. So it's basically something which explains the mathematical structure of the equations. Because, as I said, there is no physics in those guys individually. It's only, the physics is all about their differences. It's just a convenient, so essentially, I'm pretending that individual phases are well defined. Meanwhile, they are not. They are not observable. And this is precisely what allows me to introduce this modular arithmetic. I pretend that the phases are well defined, but then I immediately take into account that they are not well defined, but I know to which extent they are not well defined. They are not well defined to simultaneously adding something to all of them. That's why I understand that if I have a line, if I have a string of integers like that, the two strings are equal if they're equal modulo this string of integers. So here are two characteristic examples. So suppose we have a three-component system. As we discussed, we have three types of elementary vortices. Actually 6, because each of the three can be clockwise and anti-clockwise. But if all the three have the same sense of rotation, say +1, +1, +1, I sum them up. That's the result of summation. But since I have to compare the modulo 1, 1, 1, 1, this guy is equivalent to 0, 0, 0, meaning that if I have a system of three elementary vortices and I go far away and I go around, what I see nothing, as if there are no vortices. Yet another instructive example is if I have just two elementary vortices, like 1, 0, 0 and 0, 1, 0, I put them nearby, I go far away and see what happens. Then I cannot distinguish what I see from the elementary vortex of the third kind with an opposite sign, because this guy is equal to this guy modulo this vector. So that's kind of an interesting, an interesting arithmetic of those counterflow vortices. So somehow three of them can sum up into the zero topological charge. Two of them can sum into something which looks like an elementary guy with the opposite sign. So it's sort of signature feature of Borromean counterfluidity. So now it's time to introduce the intercomponent coupling, which Raphael was referring to. So now it's time to convert our system, which is a counterfluid, into what we call Borromean insulator. And the metal is just finite temperature phase of Borromean insulator. So this paper, once again, we are going to explain it. And essentially, what is the structure of the state which is being discussed is the following. We have three bands. We have, in my nomenclature, three fields, because each band corresponds, Cooper pair band corresponds to a field. But in addition to what I discussed, now we do not have U1 cross U1 cross U1 because of Josephson coupling, because of tunneling, because electrons can tunnel from one band to another, meaning that there is some coupling. And if this coupling is frustrating, meaning that actually the phases, the superfluid phases in each band want to be opposite. If we had just two, that would be easy, an easy game. They would be just directed in the opposite. They would have just a pi difference. But the best thing we can do with three of them is do the following. We have just a 120-degree angle between them. And now that's the structure of this superconducting phase with broken time reversal. And the broken time reversal is easily understandable, because you see, if you have the arrangement like that, the order rarely matters. You can have red, blue, black, but you can have red, black, blue. And those two cases are related to each other by complex conjugation. That's how we have actually two different ways of arranging three phases in such a way that the phase difference between them is 120 degrees. Now, if at finite temperature we have a proliferation of the global vortices which would destroy superconductivity, there is a chance, so people call it vestigial ordering, right? So when essentially you partially destroy your order, so vestigial scenario. So by this scenario, generic scenario, vestigial order or vestigial ordering, when you kind of kill part of your order but not total order, you can end up with the situation when the guys are still have a well-defined relative phases, but their global phase is disordered. And this is very reminiscent essentially equivalent to what I'm going to describe as the ground state. So here it's essentially a finite temperature phase, vestigial ordering, all this story. I really want this phase, an equivalent of this phase, to be the ground state. That's the point. So I want to see how this phase can emerge not via the vestigial scenario, but directly in the ground state. So to this end, we just need kind of a simple realization. We can take the Hamiltonian and add, and say take Hubbard model and add the intercomponent couplings, which are frustrating in such a way that the guys want, the phases want to order like that. And then that would be the order parameter, imaginary part of this guy, because the real part is supposed to be there by explicit symmetry breaking, but since the Hamiltonian is real, the imaginary part is really the order parameter, because the time reversal symmetry is broken. Otherwise, the imaginary part has to be 0. So the interesting thing, the aspect which was relating to, is supposed to explain the following. So if we have such type of an insulating phase, because we log the phase, there is no global phase, but what is left is a non-trivial way of introducing the domain wall between the two states. So those are two possible domains with our situation of broken time reversal. It can be red, blue, green, or red, green, blue. But how do we go from one to another through the domain? We need to swap two phases. But we can swap green and red, like here. We can swap green and blue. We can swap red and blue. So we have 3 types of swapping within the domain wall, meaning that we have 3 domain walls rather than 2. Now, if we have more than 1 domain walls, even within domain walls, we can have a defect, which will look like a vortex locally. Because you see, if we have one type of domain wall, another type of the domain wall, there will be a domain wall in the domain wall. So it's kind of, that's what I refer to as a quasi-topological ordering. Somehow, the phase features something beyond just 2 domains. It features some hidden structure. Some hidden structure of the phase which manifests itself in the multiple domain walls and effects like that.
Sorry, I have a question.
Yeah.
So the orientations of these vectors, are they pinned by the Hamiltonian, the only point user?
Oh, it's more than that. The orientation of those vectors make no sense, because it's essentially they make no sense by this gauge invariance. So you can rotate them, because as I said, it's just a way of expressing the ideas, because the individual phases make no sense whatsoever, only the phase differences.
Great. So when you're talking about these domain walls, they're the extended domain walls.
Yes. Yes, yes.
So when you're talking about a single defect within the domain wall, is this also an extended
Yes,
defect?
yes. That's a good question. That's a good question, because you see, if we talk of quantum mechanics, quantum mechanically, if they are very narrow, they can be quantum fluctuations. That's an excellent question, really, because those guys, if they emerge as quantum fluctuations, if they proliferate as a result of quantum fluctuations, that can actually convert 3 domain walls into 1 global. Excellent question. I'm not talking of these defects. To put it different, I want those couplings not to be strong enough so that we are really talking of extended domain walls. Excellent comment, right. So this guy has to be small enough, otherwise we will kill this kind of, because my language is semi-classical, right? Classical fieldish. Once I start talking of quantum mechanics, obviously quantum mechanically, say I can proliferate those guys quantum mechanically, and then there will be just 1 domain wall. The effect will disappear. Okay, so hydrodynamics for barometer insulators, it's very simple. I just need to add those Josephson terms, and everything will be in place. We will have a generalized form of continuity equations with those right-hand sides, which describe the intercomponent coupling. Actually, this is the most general form of the Hamiltonian. So now we know that the guiding principle is the compact gauge invariance. And if we ask ourselves the question, how do we write the Hamiltonian that is guaranteed to have compact gauge invariance, we immediately realize that we do not need to know any specifics, any specific form of the Hamiltonian. We just need to satisfy those two relations, because this is what guarantees the invariance of the Hamiltonian density upon gauge transformation. And once we know that our Hamiltonian density is supposed to satisfy those conditions, we immediately see that whatever is the form of the Hamiltonian satisfying those conditions, we are guaranteed to have those equations of motion and this property, which essentially immediately follows from those two equations. So that's the prescription how you can kind of design nonlinear hydrodynamic Hamiltonians for barometer counter fluids. So that's my conclusions. We have kind of special type of counterfluids, which we call barometer counterfluids. It's the system when we have 3 and more components. In those systems, we have n-1 phonon modes, but n elementary vortices or supercurrent states. There is a state of barometer insulator. The most interesting state is the state with broken time reversal symmetry, because it has a sort of topological-like ordering in addition to just broken time reversal. So we have hydrodynamic description of barometer states. And actually, I didn't mention it, but it's interesting to think of just multi-band superconductor, because you see, as long as the net flow is arrested in the bulk superconductor due to the Anderson effect, we can think of the bulk of the multi-component superconductor as if it's sort of barometer counterfluid, because the net flow in a superconductor is all about the surface, but the counterflow can happen in the bulk. So in principle, we can think of a multi-band superconductor if there are no Josephson coupling as a barometer counterfluid. If there are Josephson couplings, we can think of it as a barometer insulator. Thank you very much.
Thank you for your talk. We have time for a couple of questions.
I have a question about the first part of the talk.
Yeah.
You were saying that there is a jump when we have just 2 vortices versus more.
Jump in the properties, yes.
Jump in the properties. So did you think about fermions? Because thinking about vortices like 1D defects in 3D space, so there will be like...
We did not, and I'm afraid that whatever I was telling you doesn't work for, because for skirmans you need kind of high symmetries, right? It's not just U1 cross U1 cross U1 which you break, right? Because you need something else, unless you introduce something in addition to superfluid orders, because I agreed to discuss superfluid orders only which are associated with superfluid phases. For skirmans, you need something more, right? You need something which is not just because the phases live in 2-dimensional space. It's a vector, and for a skirman, you need so kind of. I'm afraid that it will be a very different story.
So when you say that there's like gauge invariance with no gauge field, right? So
Say it again. I do not need the gauge field.
right, so does that mean that there's no like long-range propagation of information between the vortices without a gauge field? How does this?
What do you mean by long, propagation of the information?
So like, you know, like in like normal electrodynamics, right? The gauge field's being sourced by a current, right? Right. And in this case,
This case is very different, of course, because in an actual gauge theory, the gauge field is a degree of freedom.
Right.
We do not have any degrees of freedom apart from our phases. Moreover, 1 degree of freedom is sort of trivial because it's gauged out. So it's a theory which is very different.
So, but then you're kind of adding by hand the fact that the phases between the different layers are correlated with one another, right?
No. Nothing is added by hand. That's the essence of the theory. We write the theory in which we pretend that each phase is a variable. But then the structure of the theory is such that that the theory allows gauge transformation. And on top of that, we say that whatever is gauge variant is not physical. It's not physically observed. And this is consistent with the equations of motion, because the equation of motions do not depend on the gradient of the phases individually. They depend on the differences. So kind of the structure of the theory is such that it is consistent with the fact that the phases individually are not observed. See what I mean? Whatever is your observable, it does not depend on the phases. So you can use any gauge you want to for the phases, as I was using kind of gauge variant way of specifying the topological defect. But in addition to that, I'm saying that whatever is gauge variant is not observable. So, or if you will, I can only make comparison modular gauge transformation. So kind of in this sense, in our case, compact gauge invariance is a tool of eliminating non-physical modes.
Maybe the last one for now.
Let me ask a quasi-experimental question.
Sure.
So, if I wanted to, I have a multi-band superconductor.
Yeah.
I think one thing that sticks out to me is that you have these grain boundaries that are domain boundaries that I'm not exactly sure what they would look like in real space, so they're really extended, but anyway.
That's an excellent question. That's precisely what they observe experimentally, or kind of sort of observe experimentally.
Yeah, that's my question. So, how would these domain walls inside of a superconductor, how is that different from just the typical multi-band superconductor picture that we would have without this description?
Okay, so
What observable is associated with this?
local magnetic fields. Local magnetic fields, because now if it's not a neutral system, it's a vortex. It creates local magnetic fields.
These are, sorry. So if I have a
Okay.
broken.
Just let me continue. So this is a vortex. If you have a standard vortex in a superconductor, the magnetic flux is quantized. They observe vortices with fractional quantum of magnetic flux, because this guy will feature fractional magnetic flux.
A well-defined fraction.
Yeah.
In small integer fraction or?
Smaller fraction. Smaller fraction. So this is precisely what they observe in this experiment. So if I think of a superconductor, multi-band superconductor with this kind of 120 degrees structure, and actually, as I say, I think of the bulk as if it's a counterflow, Baromean insulator. I'm supposed to see those structures. And those structures, as opposed to actual standard vortices, which feature quantized magnetic flux with standard quantum, those guys feature the magnetic flux, which is approximately 1/3 as far as I remember, but it's not, if everything is symmetric, it will be 1/3 of the standard magnetic flux quantum. So they see localized magnetic fluxes which do not correspond to integer quanta of magnetic flux. Quite a feature.
And so the description is those are composite objects that are due to these multiple.
Yes, they are composite objects that they are enforced of this kind of microscopic structure of three phases are related to each other, kind of blah, blah, blah. Yeah. Good question. Yeah. So
So this, I guess we can end this